Hello there. This video is for section 3.5, explaining an advanced version of the chain rule and what implicit differentiation is. Before I get started with that, I'm just going to do a couple of very brief review problems on the basic idea of the chain rule. So I'm going to be doing examples A and B on these lecture notes, where I'm just going to be doing some review of the chain rule. I'm not going to go into a lengthy description of each one, but just to get us warmed up, making sure we remember exactly how the chain rule works. All right, so for example A, I'm going to be finding the derivative. The output variable is y, the input variable is x, so I'm going to be finding dy dx. And this is sine of some stuff, sine of a thing. So the derivative of sine of a thing is cosine of that thing times the derivative of that thing. In this case, the inside thing is 4 to the x squared. So I'll write that in each of those places there. Okay, so next step here, I've done the derivative of the sine part, the outside function. That's the cosine 4 to the x squared. But I do need to multiply by the derivative of the inside function. So the derivative of 4 to the x squared, the derivative of 4 to a thing is 4 to the thing, ln 4 times the derivative of the thing. Right, in this case, the thing is what we've replaced x by. Normally, we'd be differentiating 4 to the x, but it's not 4 to the x, it's 4 to the x squared. So x squared is my, my stuff, my inside function. So that'd be 4 to the x squared times the derivative of x squared. All right, so got one more step, I think, here. We have the cosine part that we differentiated. We get this 4 to the x squared ln 2, ln 4, excuse me. And then the derivative of x squared is just 2x. Really not much for me to combine together. There are no like numbers or similar things I can combine together. So I'll just say that's where we're going to stop for this example of the derivative of sine of 4 to the x squared. All right, next example I have here is just another simple chain rule problem. I'm going to be finding the derivative of y with respect to x. Y is the outside variable, x is the inside variable, excuse me, the output variable and the input variable. So the derivative of e to a thing is e to the thing times the derivative of the thing. Okay, and the thing, just in case you want a visual sort of spotting of that, instead of e to the x, we've had e to the cosine cube root of x. So our replacement of x is the cosine cube root of x. All right, so next step, we just rewrite this e thing. And the derivative of cosine of thing, derivative of cosine x is negative sine x. Derivative of cosine of thing is negative sine of that thing. The thing, if you want to make sure, is the inside function right there, the thing that we've replaced x by. So negative sine of that thing times the derivative of that thing. Okay. Let me just clean this up a little bit. We don't really differentiate roots, cube roots and stuff. We write them as fractional exponents. Also, this minus sign, I just want to move it to the front because I don't want that to be confused with a subtraction symbol. It's a multiplying by negative, so I'll just put the multiplying by negative out front just so it's easier to, well, not get confused by. So I have the sine thing. And then I'm going to do the derivative of x to the 1/3. Cube root is 1/3 exponent. And that is just a power rule. It's not it's not stuff to the 1/3. It's just x to the 1/3. So we have no inside function. We just have the x there. So a lot of what I'm going to be spending time here is just rewriting things. I know it's a little tedious, but that is in fact one of the things math is famous for is lots of tedious steps. Derivative of x to the n, or x to the 1/3, will be 1/3 x to the minus 2/3. Subtract 1 from that exponent. And I'm going to move the two numbers together. There's a -1 in front and a 1/3 towards the end. So I'll just bring those together as a -1/3, and everything else is just going to be lined up. Not much else I can do here because they are different things. I can't really combine them together. So that is the answer for the second chain rule problem that we're doing for review. Okay, so let's start looking at the necessary information for the advanced chain rule. It's going to be here on this page, and I'm going to have to zoom in a little bit to make this a little easier to see. All right. So these problems may look easier, and in fact, they are. They're kind of one-step chain rule problems, but I'm trying to build up to a bigger concept here. So bear with me with the simple ones right here. The first one, we have sine x raised to the fourth. We have thing to the fourth. So the derivative, dy dx, outside variable, or I mean, output variables y, input variables x. So the derivative of thing to the fourth is 4 times thing cubed times the derivative of the thing. And you may know what the thing is. That's the inside sine x. Like I said, like a simpler version of the warm-up problems I did just a couple minutes ago. And derivative sine is cosine, and we're good. All right, so we don't just have to do it with sine x. We can do it with any function. We could do it with cosine or tangent or e to the x, or a combination of things like e to the x plus x. And the process is going to be exactly the same. Our derivative is going to be 4 times that stuff to the third times the derivative of the stuff, right? So it doesn't really matter what's in there. We're just going to be differentiating it like we do. So what's the inside? E to the x plus x. And so I'm going to have to differentiate. I'm going to multiply by the derivative, e to the x times x, to get the correct result. We get 4 times our e to the x plus x inside function cubed, and the derivative of e to the x plus x is e to the x plus 1. Remember your parentheses there. I'm not going to distribute anything. I'm just going to leave it like that. All right, so there's a couple examples of, thing to the fourth. All right, so here we go. Next chain rule problem I'm going to be doing is y equals x to the fourth. Remember, it doesn't matter what's inside there. It could be sine x, it could be e to the x plus x. I'm going to be doing it with x. So I'm going to be differentiating this thing. So I'm going to be differentiating dy dx, and that's going to be 4 times thing to the third times the derivative of the thing. And the thing in this case is just x. And so I'll put that there. All right, so what does that make my dy dx? Well, I get my 4x cubed times the derivative of x. Well, the derivative of x is 1. And so we get 4x cubed times 1, which, as you know, is 4x cubed. And hopefully you're saying to yourself, why are we doing all this complicated stuff when I already know the derivative of x to the fourth is 4x cubed? I'm trying to lay a foundation for a much more complicated version of the chain rule. And the key idea here is that no matter what's in the parentheses, even if you think it's already something very basic, we're going to be applying the chain rule. We're going to be applying the chain rule to pretty much everything. And sometimes you'll get things like this, dx of x, which is just going to be 1, and therefore it goes away. And sometimes you're not. So that's sort of my strategy here, is to lay this foundation of we're using the chain rule always. So as an example here, we have this fourth example where u is the function, but we're still finding dy dx. We're still finding the derivative with respect to x. So essentially what I'm doing is, let me just go one step back, is I'm finding the derivative of this side, and I'm finding the derivative of the other side, right? I want us to eventually think of derivative as an operation that we do to both sides. Like we can add 7 to both sides, we can square root both sides, we can differentiate both sides. And we need to be very specific about what kind of derivative we're doing. We're finding dy dx, so we need to differentiate with a dx in the bottom. All right, so the derivative of y with respect to x, we know is just written as dy dx. And the derivative of this thing, well, this is thing to the fourth. So once again, we get 4 times the thing to the third times the derivative of the thing. In this case, even though we're sort of thinking that, the derivative of just a single variable is 1, we're differentiating respect to x, and this is not x. Remember, x was the previous one we did over here. This was the x guy. That was x to the fourth, and when we differentiate the inside function, it was 1. And now we're differentiating the inside function. It's not x, so we're not going to get 1, right? So how do we write this? Well, we have the derivative with respect to x is our 4u cubed times the derivative of u. Well, how do we write the derivative of u? Well, you know how you write the derivative of y. We did that already. The derivative of y is just written as dy dx. So the derivative of u is written as du dx, just like that. And that is the answer we're looking for. I know it looks maybe not as simplified as you would like it to be, but that is sort of what we're working towards in terms of sometimes when we find a derivative like dy dx, our answer may have another type of derivative in it, in this case, like du dx. And just by the way, as an aside, going back to this x to the fourth problem, that was a very strange, simple problem. When I differentiate x, like when I differentiate y, I get dy dx. When I differentiate u, I get du dx. Really, when you're differentiating x, what you get is dx dx, right? dy dx, du dx, dx dx. And what is dx over dx? Well, anything over itself is equal to 1. So that's in fact why we get the 1 right here. It's really just dx dx, which simplifies to be 1. I'm not sure if that helps or not. I'm going to be writing some dx over dx's occasionally. So we know it simplifies to be 1, but I'm just going to try to set up the strategy, the pattern as we go along. All right, so let's get to a more complicated function. Suppose I have this function y equals x squared plus z squared. And once again, I'm looking for dy dx. So I'm going to be finding the derivative on the left-hand side. And I'll be finding the derivative on the right-hand side, doing the same thing to both sides, which is just find the derivative. Okay, well, the derivative of y squared, this is y to a thing, y squared, right? Not y to a thing, excuse me. This is thing squared. This is like a power rule, but we're differentiating respect to x. And if you remember, we're using the chain rule. Sometimes we get a dx dx and it's equal to 1, but sometimes we don't. In this case, we are not. The derivative of y squared, well, we know the derivative of a polynomial, of a power function, is 2y to the first power. And then we need to multiply by the derivative of the inside function, which is the derivative of y. I will box this just to make sure visually you see what's going on. That's a thing squared. So the derivative of thing squared is 2 thing to the first power times the derivative of thing. Right? We're going to apply the same kind of process right here. This is a thing being squared. So the derivative of thing being squared is 2 times that thing to the first power times the derivative of that inside function, that thing. And likewise, we'll do it with the z thing. This is going to be plus 2z to the first power times the derivative of that inside, that thing, which is just z. All right, so it really matters that we're doing ddx. Why? Because in this first example, when we're differentiating with respect to x of y, we get what's called dy dx, the derivative of y with respect to x. In the second part right here on the right-hand side, we have 2x to the 1, or just 2x, and we have the derivative of x with respect to x, which, as we know from before, is just called dx dx. And yes, dx dx is equal to 1. And lastly, we have this z part, very similar symmetrically wise. You get the derivative respect to x of z, that is called dz dx. So I'm setting this up so you can see the pattern. Each time we're just differentiating and multiplying by the derivative of the inside, whatever that inside is. If it's a variable, we differentiate by the variable. If it's a function, we differentiate by that function. You just always apply this chain rule. Sometimes the inside function is going to give you a 1, which kind of disappears, right? Like this example right here, when we differentiate the inside function x, we end up getting a 1. And when I rewrite this problem, we don't need to write the dx dx anymore. So I'll write 2y dy dx equals 2x plus 2z dz dx. And we're not quite done, my friends, because the goal wasn't just to differentiate both sides. The goal was to find, I'll write it over here, dy dx. We want to find dy dx. What we have here is 2y times dy dx is equal to a bunch of stuff. We didn't find dy dx yet, but we know algebra, and dy dx is right here. So as long as I can get rid of the stuff which is not dy dx, I solve for dy dx. And the stuff which is not dy dx is this 2y thing. So since it's a multiplication problem, the opposite of multiplication is division. I will just divide by 2y on both sides. And that will isolate the dy dx. So I get this fraction 2x plus 2z dz dx, all divided by 2y. And that is my derivative, dy dx. I found dy dx. Again, it may not be as simplified or maybe as simple as you would hope it would be, but that is the derivative. That is dy dx. As long as you know the values of all those things, we can plug them in and find an exact value for dy dx. So hopefully this is giving you a window to what the advanced version of our chain rule is going to be. I'm going to take this example and do a couple of sort of extra things with it. So I'm going to zoom out just a little bit and rewrite this equation over here on the side. So this is kind of like a bonus. I'll do a couple bonuses real quick. So no one said that x has to be the inside variable, the input variable, excuse me. No one says x has to be the independent variable, right? We could have a graph, a function where the y variable is here and you have a z variable here or anything other, letter you want. So we could find the derivative using y as the output variable and z as the input variable. So we'd be finding not dy dx, because x is not the horizontal axis, we'd be finding dy dz. So how do you find dy dz? Well, we would have to differentiate this with respect to the inside variable. I keep saying inside, with respect to the input variable, which is z. So we're differentiating both sides with respect to the input variable. In this case, if we're saying the input variable is z, maybe the instruction said z is the input variable, then we wouldn't do d dx, we'd be doing d dz of both sides. And we could differentiate with respect to any variable. We could call anything the input variable, anything else the output variable. It doesn't really matter. We just have to be clear about what is what. The process that we now do is going to be virtually the same. If I differentiate y squared, I get 2y to the first times the derivative of that y. Notice it's d dz of y, since we're doing a derivative with respect to z. On the other side, we get 2x to the 1 times dx dz. Remember, z is our, with respect to variable, our input variable. And then we get 2z to the 1 times the derivative of z with respect to z. Oh, this is the one that's going to equal 1. Now we have a dz over dz thing. And this guy over here is going to be where the sort of derivative goes away, right? Where you get a 1. And so, I'm not going to do the whole problem, but you can divide by 2y at the end to solve for dy dz, right? So to find dy dz, we would differentiate with respect to z. That's the input variable. So we have to differentiate with respect to the input variable. And then we get our big mess of stuff. that we can solve for dy dz. I'm not going to write the whole thing out, but I'll just remind you that we would just divide by 2y on both sides, and that would give us our answer for dy dz. All right, last bonus. So that was bonus. I'll do bonus. So bonus, or bonus squared. Bonus squared. Same equation, right? Y squared equals 2x squared plus 2z squared. No, not 2. Excuse me. The original equation, I immediately forgot it. Just zoom up here. Was y squared equals x squared plus z squared. So let me just keep the exact same equation. So as I mentioned a moment ago, no one said we have to use x as the input variable or z as an input variable. We can use anything we want. So I'm going to have as my last bonus is we're going to find dy dt. And you say, well, what's t? Well, t is the input variable, right? We have an input of t and an output of y. Yeah, I don't see a t in the equation, but that never stopped us before. We can differentiate things even if the variable's not in there. We're going to assume that x and z are variables that change with respect to t, right? So we're not just saying x and z are constants. We're going to say x and z are actual variables. They just move in time or move in t, and we're going to find the derivative of these things. So just in terms of what we've been doing, if we're trying to find dy dt, if we're trying to find dy dt with t as the input variable, then I'm going to differentiate with respect to t on both sides. And on the left-hand side, we got a y squared. On the right-hand side, we have x squared plus z squared. Our process is going to be the same. We're going to differentiate, multiply by the chain rule every single time. Sometimes maybe the chain rule part, goes away or simplifies. Sometimes it doesn't. The derivative of y squared is going to be 2y times the derivative of y. The derivative of x squared is going to be 2x times the derivative of x. Notice I have a dt in the bottom because that's our input variable. And the derivative of z squared is 2z times the derivative of that variable. And none of these simplify to be 1. Not a single one of them is dt. So none of them are 1, but that's okay. We're just doing math, right? Math is a bunch of symbol manipulation. So let's do that. And then I'll do the last step, just divide by 2y. So I get this fraction that looks a little bit more complicated than before, but you can see it's kind of the same thing, just that we don't have as simplified an answer as we did before. But that is the derivative of y squared equals x squared plus z squared with respect to t. In other words, that is what dy dt is for this particular equation, for this particular situation, function. Not really function, but you understand what I'm saying. Okay, so that is the idea of the advanced chain rule. Hopefully that's all making sense. All right, so we're now going to find the derivative using what's called implicit differentiation. And it's okay if you don't know what implicit differentiation is. I'll explain it right now. I'm just going to zoom in a little bit. This is the last part of our video, is doing implicit differentiation. So the first of all, we need to define what an implicit function is. So this is a function that is not solved for the output variable. Usually the output variable is y. It doesn't have to be, of course, but it's basically not solved for that y. So this is not. This is supposed to be an n. Is not. So you can see my example A over here. Let's assume that y is the output variable and x is the input variable. This function is not solved for y. I guess we could subtract a cosine, do the inverse sine of both sides. It's going to get quite messy pretty quickly. And even if we could do it, for example, A, there are definitely problems in which we couldn't even do it. We don't even know the math to solve or isolate the y or the output variable, whatever the output variable is. The thing is, as long as we understand the chain rule, it does not matter. We can differentiate both sides and we can solve for dy dx or whatever derivative we're looking for, regardless of whether it is explicitly solved for y or whether it's implicit, where y is somewhere in there, but not necessarily solved for that output variable. All right, so let me demo this, and I'm going to be using the same kind of language we did in this previous problem with the y squared equals x squared plus c squared. So I'm looking for dy dx. So maybe the directions should be clear, but I'll write them here. I'm going to find dy dx. It doesn't matter what derivative we're looking for because it tells us what to differentiate with respect to. In this case, I'm going to be differentiating with respect to x. So I'll differentiate the left-hand side with respect to x, and I'll differentiate the right-hand side with respect to x. As so. Oops, I gotta put this left-hand thing in there too. Sine y plus cosine x. So differentiating both sides with respect to the x variable. The x variable was right here, the input. So that's why I differentiate respect to x. So now I just apply all of my chain rule that I learned, sort of the what I call the advanced chain rule. So the derivative of sine y is cosine y times the derivative of that y. And I'm using ddx as always because ddx was x was my input variable. The derivative of cosine x, the derivative of cosine x is going to be minus sine x times the derivative of x. On the other side, we have the derivative of x cubed minus x. The derivative of x cubed is 3x squared times the derivative of x. And the derivative of minus x is minus 1 times the derivative of that variable. Okay, so we get cosine y. What's the derivative of y with respect to x? Well, it's written as dy dx. I think I forgot my equal sign somehow. Oh, this is supposed to be equal sign right here. Oh, no, that's a minus sign. My equal sign's over here. All right, sorry, I just got confused for a moment. Minus sine x times ddx of x. So this is minus sine x. The derivative of x with respect to x is dx dx. Or as you all know, this is equal to 1. Continuing on now on after the equal sign, now that I found it, we get 3x squared times dx dx and minus 1 times dx dx. And these dx dx's, as you already know, are going to 1. They divide or simplify. And you may be asking yourself, do I really have to write the dx dx? No, you don't have to write the dx dx. I'm just trying to illustrate what's going on here. I'm not trying to hide the fact that that d thing goes away. It is the chain rule every single time. It's just that in several situations, it's going to disappear because it equals 1. And when you multiply anything times 1, you don't see the 1 anymore. So I'm just trying to be very clear about what's happening, even though when you're doing your own work, you might want to maybe shorten it a little bit if you're more comfortable with it. But you know, you do you. I'm trying to explain this. I do need to solve for dy dx, and dy dx is right here. Here's my equal sign that I lost before. In order to solve for something, in order to solve for a variable, in this case, in order to solve for dy dx, I need to get the dy dx on one side, and I need to get everything else on the other side. So my dy dx is attached to this cosine y through multiplication, but it's got a subtraction after that, subtracting sine x. So I can get rid of that minus sine x just by adding sine x to both sides. Minus sine x plus sine x is going to equal 0. That's why that goes away. And I don't really have much else to simplify. So what I have here on the left-hand side, I'm going to have to go over here because I'm out of space. I have cosine y dy dx. I have my 3x squared times 1. I have my minus 1 times 1, and I have my plus sine x. So now I moved everything to the one side that doesn't have dy dx in it. And my last step is just to divide by cosine y. So I divide by this thing right here. And that gives me dy dx. Oops. Let me put that back in blue. So dy dx is equal to this thing, 3x squared minus 1 plus sine x, divided by the coefficient, which is cosine y. Right? We just divided by this on both sides, and we got this as our dy dx derivative. So that is called implicit differentiation. I had a function, it didn't say y equals, it just had a bunch of stuff with y in it, and I can still find dy dx. Right, if you haven't been doing so, reminder, you can always pause the video and try stuff now that we've done an example of implicit differentiation. If you haven't done so already, maybe it's a good time to pause and see if you can find the derivative, the dy dx of example B. Again, my directions aren't very clear here, but again, I want to find dy dx. All right, well, hopefully you had a chance to pause the video and give that a go. I'm going to be differentiating the left-hand side with respect to x, and I'm going to be differentiating the right-hand side with respect to x, because I'm looking for dy dx. If I was looking for dy dt, I'd be differentiating both sides with respect to a t, or whatever variable that I want. Now I'm just applying the chain rule, multiplying by the derivative every single time. The chain rule as many times as I possibly can until I get down to the derivative of a variable. The derivative of e to the y is e to the y times the derivative of y. The derivative of y cubed is 3y squared times the derivative of y. The derivative of tangent x is secant squared x times the derivative of x. Derivative, chain rule, derivative, chain rule, derivative. I'm just doing every time. So over here, I'm just going to write it in a little more simplified form to see. I have e to the y dy dx. I have a 3y squared times y. No, 3y squared times the derivative of y, which is 3y squared times dy dx. Almost made a mistake there. And over here, I have secant x squared times 1, because the ddx is just, dx dx is just 1. All right, I want to solve for dy dx. Dy dx is here, and it is also here. There's two dy dx's. So when you have multiple copies of the object you're looking for, you need to gather those together. They're both already on the same side of the equal sign. In this case, they're on both on the left-hand side of the equal sign, but they have different coefficients. And so the standard method, there are different ways of doing it, but the standard method is just to factor. So I factor out a dy dx, and then here I have e to the y left over, and I have 3y squared left over. Right-hand side is just going to be secant squared. And as long as I divide by this thing, this multiple thing, I'm multiplying by this creature in parentheses. So the opposite of multiplication is division. So as long as I divide by that, then I can isolate dy dx. And that is my goal, is to find dy dx. So when I get dy dx by itself, it's this fraction, secant squared x over e to the y plus 3y squared. That is my derivative. That is my dy dx using implicit differentiation. All right, how about that? How about that? All right, so I do have some more examples of implicit differentiation. I have examples C and D here. Again, I'm going to ask you guys to try these before you look at my solution. So please pause and try this. I'm going to pause the video myself and write out my solutions and just explain them to you when you come back, or when I come back as well. So I'm not going to show you all of them in real time. I'll just write out the solution and explain the steps that I did to arrive at that. All right, so see if you can get a solution and then compare to what my result is as well. Okay, so welcome back. I have my solutions written out, and I'm going to go through and explain them step by step. So I took the derivative with respect to x on both sides for example C, and that looks like this: d dx on the left and d dx on the right. The derivative of e to a thing is e to the thing times the derivative of the thing. So I get e to the xy times the derivative of xy. On the right-hand side, I have a sum. So I differentiate the x, which is 1 times the derivative of the variable x. And then I add to that the derivative of y, which is 1 times the derivative of that variable, d dx of y. Okay, so both sides have something interesting. Left-hand side, we have this e to the xy, and we have the derivative of xy. Xy means x times y. And to differentiate when two things are multiplied by each other, we use the product rule. So I just kind of wrote out the product rule without actually doing much of the derivatives. It's the derivative of the first times the second plus the derivative of the second times the first. That's our product rule. On the right-hand side, we have a lot of simplification. The derivative of x is just 1, and the derivative of y is written as dy dx. So we end up with something looking like 1 plus 1 times dy dx, or just 1 plus dy dx. On the other side, we have to differentiate using the product rule. The derivative of x is just dx dx, or 1, times y, and the derivative of y is dy dx times x. So I did my product rule right here. And then, of course, that's times e to the xy on the outside. I do have to solve for dy dx. There are a couple of copies of dy dx. There's one of them right here. There's one of them right here. So I have to gather them together on the same side of the equal sign to be able to solve for them. First thing I did is I just distributed. I multiplied things out on the left-hand side. I got e to the xy times the first part, which is y, and then e to the xy times the second part, which is x times dy dx. Yeah, I just wrote them in different order. Just, I guess in habit, I wrote the letters together and the derivative afterwards. On the right-hand side, I just have 1 plus dy dx. I kind of ran out of room, so I had to go to the next side, next column. I do need to get all my dy dx's on one side. So this dy dx, I'm going to subtract them both sides just so I can get all the dy dx's to that left-hand side. And this first thing, e to the xy times y, has no dy dx's in it. So I subtracted that to the right-hand side. So I subtracted by this e to the xy times y on both sides, and I subtracted by dy dx on both sides. So going over to this next column, that gives me on the left-hand side my x e to the xy dy dx minus the 1 times dy dx. And the right-hand side, I had the 1, and then I minus this y times e to the xy. Oops, a little shaky cam there. All right. Now that we have all the dy dx's on one side, we need to factor, get them together. So I factor a dy dx, and I'm left with some stuff inside that I just divide by on both sides, and I get my derivative dy dx. So that's my big fraction that represents the derivative dy dx. All right, the other example that hopefully you had a chance to try was this one down here. Example D. So once again, I differentiate both sides, differentiate the left-hand side with respect to x, differentiate the right-hand side with respect to x. I'm going to, again, just be kind of doing my strategy of doing derivatives. So I'm going to write out a lot of derivatives before actually taking the derivatives, a strategy that I've suggested in the past. As these problems get more and more complicated, it's just harder and harder to keep track of everything in our head about what's been differentiated and what still needs to be differentiated. What is the inside part, etc. So you do you, but my suggestion is kind of write stuff out so that you don't, miss any pieces of it. So the derivative of x sine y, this is again the product rule, because x times sine y are two different things being multiplied, two different functions being multiplied. So I differentiate. So the derivative of these two things right here would be the derivative of the first times the second plus the derivative of the second times the first. So that's just the standard product rule. Notice I didn't do any derivatives yet. I'm just writing it out. I have to differentiate e to the x and add that on. And then I differentiate the right-hand side. I haven't done that yet either. So derivative of y cubed. So now I'm going to start doing my derivatives. The derivative of x with respect to x is just dx dx, or 1, and you get the sine y. The derivative of sine y is cosine y times the derivative of y, and that's multiplied by x. And the derivative of e to the x is e to the x times the derivative of x. Again, I'm just doing my derivative rules. I'm doing the chain rule every single time. Many of them are going to go away. Many of them are going to be like dx dx, like this one right here. And you can, not write it if you don't want to. As I said before, I'm going to write it out a few times just so people can see what's happening here, that it doesn't just disappear because I want it to. It disappears because it's equal to 1. And when I multiply by 1, it doesn't have any effect on the rest of the problem. On the right-hand side, to differentiate y cubed, that's 3y squared times the derivative of the y, multiplying by the variable, again, using the chain rule. All right, so now I just have to clean things up. Notice that there are a couple of copies of dy dx. There's one of them over here. Oops, that was supposed to be in a different color. Let's try blue. There's a dy dx over here, and there's a dy dx over here. I guess I cleaned it up a little bit here, so I got rid of the 1, and I just simplify things a little bit. The dx is 1. So I noticed that because I have dy dx on different sides, I'm going to have to subtract the dy dx on one side to get on the other side. I elected to get rid of the dy dx on the left-hand side and move it to the right-hand side by subtracting the same thing on both sides. So I'm subtracting the cosine y dy dx on both sides. That puts all the dy dx's on the right-hand side. You may have put it the other side, doesn't matter. The answers will be equivalent. All right, so what's left over here on the left-hand side is my sine y, my e to the x times 1. So I just have sine y plus e to the x. On the right-hand side, I have all my dy dx's times their coefficients. I factor out my dy dx, and then I divide by that, parentheses, the thing that's being multiplied by the dy dx, and that solves for what dy dx is. All right, well, this is the end of the video. Those are some examples of implicit differentiation, and of course, utilizing an advanced version of the chain rule in order to get our derivative. I hope you have an enjoyable day, and I hope I can see you sometime soon, hopefully on Zoom or at least in the next video.